Hi, in this video, I am going to teach you how to solve linear Diophantine equation and how to use linear Diophantine equations in solving certain numerical problems. A Diophantine equation is any polynomial equation in one or more unknowns or variables, which is to be solved in the set of integers. Now, the Diophantine equation is named after Diophantus of Alexandria. This mathematician authored a series of books called Arithmetica that deals mainly on solving algebraic equations. This is a page in the Latin translation of Diophantus Arithmetica by Claude Gaspard Bachet in 1621. These are some examples of famous Diophantine equations. Probably one of the most famous and one of the most classical Diophantine equation is the Pythagorean Triples or the Pythagorean equations x squared plus y squared equals c squared. Now, integer solutions of these equations are called Pythagorean Triples, which are actually the length of the sides of a right triangle. The equation x to the n plus y to the n is equal to c to the n, also known as the Fermat-Last theorem, states that the equation for n greater than or equal to 3 has no positive integer solution. But Fermat failed to show the proof of his claim. Fortunately, this is already proven by Andrew Wiles in 1995. Another famous Diophantine equation is that of Ramanujan and Hardy, which is w cubed plus x cubed is equal to y cubed plus c cubed. So the task is to find two different ways of expressing a number as sum of cubes. One of the most famous solution is given by Ramanujan to Hardy in 1917. Which is the value 1729. This can be written in two ways as sum of cubes. One is 12 cube plus 1 cube and the other is 9 cube plus 10 cube. That's why this number is more popularly known as Hardy-Ramanujan number. Actually, this equation has infinitely many solutions. Another equally famous Diophantine equation is the Pell equation, which again were studied extensively by Fermat and by an Indian mathematician, Brahmagupta. So the equation is x squared minus ny squared is equal to plus or minus 1 for some positive integer n. All of these are examples of Diophantine equation that paved the way of finding solutions of different kind of equations with integer solutions. Now, the most basic Diophantine equation is the linear Diophantine equation. So, a Diophantine equation of the form ax plus by equals c, where a, b, and c, the coefficients are all integers, is called a linear Diophantine equation. Now, a Diophantine equation may or may not have a solution. For example, this Diophantine equation 3x plus 6y equals 18 has a numerous solution. Actually, it has infinitely many solutions. Few of the solutions are as follow. We know that 3 times 4 plus 6 times 1 is 18. Similarly, 3 times 6, 18 plus 6 times 0 is 18. 3 times 0 plus 6 times 3 is 18. 3 times negative 4, negative 12 plus 6 times 5, 30. Negative 12 plus 30 is 18. So, all of this pair of integers 4, 1, 6, 0, 0, 3, negative 4, 5 are solutions of the Diophantine equation. And there are a lot more. There are infinitely many more solutions of these equations. Now, on the other hand, if we look at the equation 2x plus 4y equals 17, we can see that the left-hand side of the equation is always even because of the coefficients 2 and 4. On the other hand, the right-hand side is always odd. 17 is odd. So that means that the left-hand side will never be equal to the right-hand side. So that means this Diophantine equation obviously has no solution. So to solve linear Diophantine equations, we're going to need the following theorem. The linear Diophantine equation ax plus by equals c has a solution if and only if d divides c. Here, d denotes the GCD of a and b. Now, if x sub 0 and y sub 0 is a particular solution of this Diophantine equation, then all other solutions are given by the expression x equals x sub 0 plus b over d times t, and y equals y sub 0 minus a over d times t. Take note that since d is the GCD, then b over d is an integer, and so as a over d. So that means this collection are integer solution of the linear Diophantine equation for any arbitrary integer t. As a consequence of this theorem, if the GCD of AB is equal to 1, then we can just substitute the value d equals 1 in our solutions so that we can now have the solution x equals x sub 0 plus bt and y equals y sub 0 minus at if x sub 0, y sub 0 is a particular solution of this Diophantine equation. The steps are really simple. Going back to the theorem, we can see that there are two things that you need to do. First, you need to determine the GCD of the coefficients. Now, once you were able to determine the GCD of A and B, all you need to do is determine whether D divides C. So, if D divides C, then the equation has infinitely many solutions. Otherwise, it does not have a solution. Now, for us to determine all the solutions of this Diophantine equation, we need to find a particular solution. And that solution can be determined either by brute force or you can use the expression for D. Of course, we know that since D is the GCD of AB, then we can always express D as linear combination of the numbers A and B. So that means once we know the linear combination of D in terms of A and B, so let's say we have a particular expression AX prime plus BY prime to be the linear combination of D in terms of A and B. And since D divides C, so we can find an integer K such that C is equal to D times K. So all we need to do is to multiply this expression with K to get C. So we have C, which is equal to dk, is now equal to KAX prime plus KBY prime. So what does this tells us? This tells us that a particular solution is A times KX prime. This is now our X sub 0 plus B times KY prime. This is now our Y sub 0. So from here, we can now use this formula to get all the other solutions. So this particular method requires us that we need to be able to express D as linear combination of A and B. There are a lot of ways or techniques for us to do that, but the best way is to use the Euclidean algorithm. So let's have some examples. Suppose we want to find all integer solution of the linear Diophantine equation if it exists. So again, tingnan natin kung ano yung steps na kailangan natin para makuha yung solution. Una, kailangan mong malaman kung may solution ba or wala. So paano mo malalaman yan? Kukunin mo yung GCD ng A and B. Now, kung yung GCD ng A and B, dinidivide niya si C, then you have a solution. Infinitely many solution. Kung si D, hindi niya dinidivide si C, then no solution. So that's the first step. Find the GCD and then determine whether a solution exists or not. si D na GCD ni AB, dinidivide ba niya si C or hindi? Kung dinidivide siya si C, then may solution. Kung hindi niya dinidivide si C, edi walang solution. So, ano yung next step? Ang next step is to find a particular solution. So, paano natin ulit hahanapin yung particular solution? Well, you can do it by brute force. You can guess a values of x and y that will satisfy the equation. But of course, that's not a very nice technique. Some equations will give you a hard time finding particular value of x and y that will satisfy the given Diophantine equation. So the best way to do it is to express D as linear combination of A and B. So what you want is to express D as linear combination of A and B. So we can do this because D is the GCD of AB. So we always can find values of x and y such that D is equal to AX prime plus BY prime. Now the surest way, yung pinakasiguradong way para maka-arrive ka in that linear combination, kung gagamit tayo ng Euclidean algorithm. If you remember sa Euclidean algorithm, by solving the GCD and then using back substitution, we can eventually express D as linear combination ng A and B. So once meron ka ng specific solution, since D is now a linear combination of A and B, and since D divides C, you can always find a K such that D times K is equal to C. So all you need to do is to multiply K in this equation so that you can arrive with dk is equal to A x prime K plus B y prime K. Ito ngayon yung iyong x sub 0 at ito ngayon yung y sub 0. Now that you have particular solution, you can now use the formula given by the theorem. So again, what's the formula given by the theorem? That's x sub 0 plus b over dt for x and y sub 0 minus a over d times t for y for any arbitrary integer t. So again, there will be infinitely many solution for linear Diophantine equation if D divides C. Okay? So let's go back to our problem. Now, yung unang problem natin, 172x plus 20y equals 1,000. So again, the first thing to check is to determine whether the GCD of A and B divides C. So in our expression, yung 172, yun yung magiging A. Yung 20, yun yung magiging B. Yung 100, yun yung magiging C. Yung 172 can be factored as 2 times 2 times 43. On the other hand, yung 20 can be factored as 2 times 2 times 5. The prime factorization of 172 is 2 squared times 43, while the prime factorization of 20 is 2 squared times 5. Clearly, the GCD is equal to 2 to the 2. So we have GCD of 172 and 20 that will denote our D is equal to 4. This implies that since 4 divides 1,000, we can now conclude that the linear Diophantine equation has a solution. So how do you find particular solution for this linear Diophantine equation? Again, you can try brute force and try to find a possible combination of integers x and y that will result to a solution. For example, you can try 172 times 0 plus 20 times 50 equals 1,000. So that's a possible solution. But of course, gusto natin yung technique natin will apply to all. So instead of doing or finding the solution by brute force, we will employ Euclidean algorithm. So again, Euclidean algorithm is performed to find the GCD of two integers. So how do we perform the Euclidean algorithm? First, we get the bigger number, and then we divide it by the smaller number, and we try to find the value of the quotient and the remainder. So 172 divided by 20 is 8.6. So more or less, you can get at most 8 times 20. So that's 160. So the remainder is 12. So 172 can be written as 8 times 20 plus 12. So this time you're going to get 20 and move it here. So we have 20 equals. So now we're going to get the remainder divided by 12 plus the remainder is 8. So we will express this as 1 times 12 plus 8. Next, we will now get 12 and divide it by 8. So 12 divided by 8, obviously that's 1 times 8 plus the remainder is 4. So this is 1 times 8 plus 4. This time we're going to use 8 equals 2 times this is 4 plus 0. Since we now have a 0 remainder, that means the algorithm is done. We now have the last remainder as your GCD. So how do you express GCD in terms of the original value A and B? So starting from this, we get 4. We express this in terms of the other. So we will transpose. So that's 12 minus 1 times 8. Now we are done with this equation. Next is to express 8 in terms of 20 and 12 using this equation. So we have 4 equals 12 minus 1 times, this time 8 is 20 minus 1 times 12. To simplify, we have 12 minus 20 plus 12. So we have 2 12, so that's equal to 2 times 12 minus 20. So do not simplify this value. Remember, what we want is to express for in terms of the original values A and B. So what we're doing is just we're substituting these values here. So those are the remainders that we get a while ago. So you do not evaluate 2 times 12 to get 24. You just treat them as somehow like a variable. So tapos na tayo dito sa equation na to. So this time, ang papalitan naman natin yung susunod na remainder, which is yung 12, gamit yung equation na to. So this is equal to 2 times, sabi sa unang equation, 12 is 172 minus 8 times 20. And then, copy minus 20. So again, do not evaluate the value, but just simplify them like variables. So, hindi natin evaluate yung 8 times 20 while keeping 20 and the value of 72. So, this is equal to 2 times 172 minus 16 times 20 minus 20. So, that gives us 2 times 172 minus 17 times 20. In short, na-express natin yung 4 in terms of A and in terms of B. So, this is now our x prime and this is now our y prime. So, all we need to do now is to get 1,000 on left hand side. So, we know that 4 divides 1,000 and for us to get 1,000, 1,000 is equal to 4 times 250. So, that means all we need to do is to multiply the entire equations with 250. This will now imply that 4 times 250 is equal to 172 times 2 times 250 plus 20 times negative 17 times 250. So, simplifying, we have 1,000 equals 172 times 500 plus 20 times 17 times 250. or that's equal to negative 4,250. So this now gives us the value x sub 0 and the value y sub 0. Now using this particular solution, we can find all other solution using the formula. Again, the formula for x is equal to x sub 0 plus b divided by d times d, and the formula for y is equal to y sub 0 minus a divided by d times t, where t is any arbitrary integers. So we have 4x that's equal to 500 plus b is equal to 20 divided by 40, or that's equal to 500 plus 5t. On the other hand, we have y equals negative 4,250 minus a is 172 divided by 4t, or that's equal to negative 4,250 minus 172 divided by 4, so that's 43t. Again, here t is any arbitrary integers. For any value of t, the pair x and y given by this equation is a solution to our Diophantine equation. So, tingnan naman natin ngayon yung second example. Sa second example, we have 54x plus 21t equals 906. So, don't be confused. Yung second variable natin dito, yung t, that will now play the role of y. So, yung 54x, that gives us the value of a. Yung 21t, that gives us the value of b. And then the constant will give us the value of c. So, we have a equals 54, b equals 21, and c equals 906. Easily, we can factor 54 as 2 times 3 cubed. On the other hand, 21 is 3 times 7. So this means, using the canonical forms of the number 54 and 21, we can easily deduce that the GCD of 21 and 54 is 3. Clearly, since the sum of the digits of 9 and 6, so it's a technique on finding divisibility by 3. So dahil ang sum ng 9 and 6 is 15, and 15 is divisible by 3, so ibig sabihin, 3 divides 906. Now, ano ibig sabihin? Pag ang GCD dinidivide yung C, ibig sabihin, there's a solution. So, ano yung next step? The next step is to determine a particular solution. Again, kung madaling kumuha ng linear combination, mga value ng x tsaka ng t, such that masasatisfy yung equation na to, then you can use that as your initial solution. Pero kung mahirap hulaan, mahirap gamitin yung brute force para manghula ng value ng x and t, pwede naman gumamit ng Euclidean algorithm. So, starting with 54, so ang gagawin mo lang, kukunin mo lang 54 divided by 21. So, 54 divided by 21, that's 2 point something, 2.5 something. So, that means yung 54 can be written as 2 times 21. So, that's 42. Remainder is 12. So, now you move 21 here. And then you move 12 here. So, 12, 21 divided by 12. That's 1 point something. So, that's 1 times 12 plus 9. So, you move 12 here. 12 is equal to, you move 9 here. So, 12 divided by 9, 1 point something. So, that's 1 times 9 plus a remainder of 3. This time, you move 9. So, that's 9 equals, and then you move 3. So, 9 divided by 3, exactly 3. So, that means the last remainder is 0. So, the last non-zero remainder becomes the GCD. Well, we already know that 3 is indeed the GCD. But we need the Euclidean algorithm so that we can express 3 in terms of 54 and 21. So, first, we're using this last non-zero remainder to express 3. So, we have 3 is equal to 12 minus 1 times 9. Again, we don't evaluate 12 minus 1 times 9. We're going to keep the value of 12 and 9 and then substitute the values from the preceding equations. So we're done with this equation. So the next is to use this time the second equation. So the second equation gives us the value for 9. So this is equal to 12 minus 1 times 9 is 21 minus 1 times 12. So we're keeping 12. We're not evaluating 12 and 21. So whatever remainder that we have, yun yung kinikip natin yung value. So we can simplify 12. So this is 12 minus 21. So that's 1 times 21 plus 1 times 12. So now you have 2 12. So that's 2 times 12 minus 21. So we're good with the second equation. The last thing to do now is to substitute the first equation. So we can get the value for 12. So we have 2 times 12 is 54 minus 2 times 21. Minus, just copy 21. So this is equal to 2 times 54 minus 4 times 21 minus 21. So all in all, we have 521. So that's 2 times 54 minus 5 times 21. So we were able to express 3 in terms of 54 and 21. Now, the next step is to find a particular solution from this expression. So how do we do that? So we get 3. We know that 3 divides 906. So we can express this as 906 is equal to 3 times 302. So that means for us to get 906, we just need to multiply this whole expression with 302. So we have 906 is equal to 54 times 604 plus 21 times 302 times 5. Or 1,510. So we now have the value x sub 0 equals 604 and the value y sub 0, so this should be negative 1,510. From here, we can use the formula to get an expression for x and y. So again, the formula is given by the expression x equals x sub 0 plus b over dt and y equals y sub 0 minus a over dt, where t are any arbitrary integers. So let me write again the value of a. The value of a is 54. The value of b is 21. And the value of c is equal to 906. So this would imply that we can write x equals, so we get x sub 0, 604 plus 21 divided by 3 gives us 70. And y equals, so y sub 0 is negative 1510 minus a is 54 divided by 3. So that gives us 18 for all arbitrary value t. Now, in our original problem, the variables are x and t. So to fix the solutions that we have, all we need to do is to change variables from y to t. But here, our arbitrary variables is using t. So we will also change that to another arbitrary variables. So ang gagawin lang natin, papalitan natin ng variable natin na y, gagawin natin t, tapos yung t, gagawin natin other variable, say k. Papalitan lang natin ito ng k, papalitan lang natin ng k, so that we meet the requirement of the original problem where the given is x and t. So we have x equals 604 plus 7k, and this time t equals negative 1510 minus 18k. K is any arbitrary integer. So this now satisfy the Diophantine equation. Let's look at our next example. 5x plus 18y equals 48. So in this example, the value of a is 5, the value of b is 18, and the value of c is 48. Very easily, we determine that the GCD of 5 and 18 is 1. Now, of course, 1 always divides 48. So, we already know that this has a solution. Now, according to our theorem, all we need to do now is to find particular solution and then substitute that particular solution in our formula for x and y. So all we need to do is to express 1 as linear combination of 5 and 18. So if you can do it by brute force, it's okay. If not, if it's hard to find values, you can always use Euclidean algorithm. But in our case, we can easily guess the linear combination. For example, 5 times 7 is 35 and 18 times 2 is 36. So that means if we make it negative 7, so it's negative 35 times 18 times 2 is 36. So this particular combination gives us a particular solution. So we have x sub 0 equals negative 7 and y sub 0 equals 2. Now, all we need to do is to substitute the value of the particular solution in our equation. X equals x sub 0 plus bt and y equals y sub 0 minus 80, where t is any arbitrary variables. So this time, we no longer need to divide it by d since d has value equals to 1. So we have x equals negative 7 plus b is 18t and y equals, so we have y sub 0 is 2 minus a is 5t, where t is any arbitrary integers. So ganun lang po kadali yung pag-solve ng linear Diophantine equation. So pag given tayo ng ax plus by equals C. Ang step 1 is to determine the GCD of A and B and to answer the question whether it divides C. So if D divides C, then we have infinitely many solutions. On the other hand, if D does not divide C, then we have no solution. Now, what if we have infinitely many solutions? So what would be the next step? So the next step is to express D as linear combination of A and B. So either you do that by brute force or you use Euclidean algorithm. So syempre ang suggestion ko, kung medyo malaki yung value, always use Euclidean algorithm. Once may value ka na ng D, and since D divides C, then you can now find a value K such that C is equal to D times K. To get your particular solution, all you need to do is to multiply this equation by k. So you have dk equals ax prime k plus b y prime k. This now is your initial solution. So you have x sub 0 and y sub 0. So now that you have particular solutions, x sub 0, y sub 0, the last step is to substitute the values in the equation. X equals x sub 0 plus b over dt and y equals y sub 0 minus a over dt. Here, t is any arbitrary integers. And this gives you a solution for your linear Diophantine equation. In our next video, I will teach you how to use linear Diophantine equations in solving certain numerical problems.